recording.
Turn on the video recording.
Okay, go ahead, Hussein. You are on.
Okay, good morning, everyone. My name is Hussein Al-Azawi, and I'll be talking about the structure of the supercomputer today. We have a few slides, and I come from the University of New Mexico. I work there as a network administrator. Well, that's what I started doing at least over there. And here in the background, you can see the Sandia Mountains, which we are so proud of. It's like 2,000 feet of sea level. This is our agenda. So it's a very short topic, try to make it easy and simple. And I'm sure like many of you guys know way more than we have this. So this is for the introductory. So here is a little about my center. We are the biggest public center.
What do you define as gain?
Your talk louder.
Talk louder.
Okay, I will try.
More.
More.
Scream at us.
Outside.
Okay, so UNM's HPC Center, we started in the 90s, and then we were part of the Maui HPC Center at the time, and then from there, it became the biggest public center at the state of New Mexico. In 2000, we edged Sandia Labs to build our first in production fieldwork cluster, and that is supposed to be the first ever in the world. Now, most of our usage comes from nuclear material science, like astrophysics and genome sequencing. And as I mentioned, I started as a network admin in 2014, and then after that, I started doing more storage, more HPC related, and then I got into virtualization. And right now, my research, which is my part-time PhD that I'm doing on the side, is on virtualizing other systems. So that's a little part what I do. And then we are here to talk about supercomputers. So what is a supercomputer? It's really just like a big collection of traditional machines that we use in businesses on daily, little bigger than the daily usage machines that we have in our laptops or systems. But that collection altogether, it gives you like a very massive power that you can process data and analyze and build like things that we cannot do with our daily machines. Then Summit. And so this is the biggest and fastest supercomputer on Earth at this point. At least this is this is true until like I would say November last year. So this was announced at the top 500, which I think will be refreshed like this month sometime. Looks nice. It was built with IBM. And then why? So why do we need to build supercomputers? Like in today's technologies, what we have today is what we have. But like if you want to build materials and like new equipment or test like nuclear or whatever other like genome sequencing, all of these things, it would take us hundreds of years if we want to try to do it on our personal computers. So we build all of these big machines, and then the other thing is scaling out our computing power, because like at this point, most load. Okay. Yeah. So at this point, most load is not applied, or like it's almost dead. So the only way for us to expand on these is to build more powerful machines by adding more and more nodes and cores, memory, all of that to process at the same time. And then this would help us increase, like by order of magnitudes, the computing and research output that we are processing. So we all hear in terms of big data, machine learning, all of these, and all of these are like hungry. All of these applications are hungry for computing power. And then, as I mentioned before, like when you're dealing with nuclear reactions, you probably want to test that nuclear reaction when on the ground. So you need to try to look like more like in a virtual space. From there, we look at the challenges of supercomputing. So as we all use, like this become more like a tradition at this point. So money can be got all the money in the room. So if you want, you can give us more resources so we can build bigger or faster supercomputers. If he doesn't, then we are in big trouble. Staffing. So like, we've been trying to hire for so long, and it's a big problem. Like one of our biggest problems, like sometimes it's hard to tell which is harder to get more funding, or is it to get like to find the best staff that you can work with, considering the limited funding that you have. So like once we interviewed for a student position, and we had 50 students apply, and we interviewed all of 50 students, and like it was a mess. Like we couldn't hire any of these guys, and we ended up in all of these graduate kids. So we ended up at the end like just looking at one of the CS classes, and we picked undergrad. It was so good. I Same thing with full-time positions, and the reason is, as we heard yesterday, like most of us fell back into these positions, like you were not planning. There is not a career path that is clear yet for these titles. Even our job titles, they talk about, like sometimes it's an HPC engineer, no wait, you cannot use the word engineer or an engineer, and then they add you as a network analyst, system analyst, just as admin. Is it consulting for the admin? And then other provinces, like which I guess we've seen all days, power, space, cooling, uh, like the power that a supercomputer, like we talked about summiting here, like the power that this machine uses, it can power about 12 cities, each one of 100,000 people. So like that's a lot of power. And today they are trying to build much cleaner systems that you can process data without like causing a lot of harm or reducing the expenses of these. And we can see this at the supercomputing competition. So every year they have at SC a competition between student teams who compete to beat the benchmarks and at the same time with the minimums, like with the lowest energy consumption. Um, But like in reality, don't we build all of these machines just to build another matrix, like a big one, or maybe the matrix. But like yeah, so all of this is about computer simulations. We need these simulations for our abstract models so we can represent them in the virtual space, and we can study the results of these before we build it in reality. And that ties to parallel computing. So all of these nodes in the computers, like when you talk about hundreds or thousands of nodes and cores all connected together, they need to work in parallel to process all of your data at the same time, or what makes it look like it is being processed at the same time. So we can see this. I don't know if you've seen recently on social media where they have cell phone farms and they connect all of these cell phones in like on racks and racks, like all of this room is surrounded by racks and it has cell phones on it, and all of these cell phones are generating social media content and likes and all of these things. So just that's like a small example of how people can, like, what do we get out of that? So like in real life, what we deal with every day, like Instagram, Facebook, all of these applications, people use even a small device like a cell phone, which was like 20, 30 years ago. That can be an example of that. And then when we talk about this, we have multi-threading and multi-processing. So multi-threading involves processing in the same memory, well, like inside the same machine, while multi-processing goes about processes being processed in parallel within the same node, but it can be across the nodes and be through like a special network. Um, then this brings up the discussion of analytical and creative. So to design a supercomputer, there are basic steps that we all know and we can talk about, and then there are other.
Still audio problems. Keep going. I'll see what I can do. Keep talking.
So you hold it.
Yeah, see what happens if you hold it right up to your mouth with your hand. Sorry, I'll just take it. Yeah, it's easy. Put it on. That frightens me. Keep talking. You're doing great.
So yeah, like as the debate goes, where
Lost the.
so can you view the audio at least?
Right now, the video is frozen.
Honestly,
Yeah.
the audio.
I'm worried that there's a problem with the
About
laptop,
the same as with the-
so I'm going to swap in my laptop.
That's why we're saying kind of speak up, speak loud, clear.
I'm going to use my.
Yeah, it does.
Turn off your mic.
Yeah.
Okay. Sorry for this. Okay, and I believe I have your slot. Where we can get it then. Yeah. Oh, there we go. Let me just download real quick. Oh, actually, I have one folder. Download. Now it's done, is that?
Yeah.
Okay. Right, and there should be
So I can hear myself.
yeah, so you need to shut off everything on yours.
Somebody just.
Okay.
Okay, is it all set? Okay, sorry about that.
Oh, there we go.
Okay, is it working better?
But let's, let him talk.
So yeah, we are doing another test. We switched computers as we are presenting. So let's see if this makes it better for you guys.
Is that working?
That sounds good.
Waiting to hear some response.
What do the folks in TV land think? Hussein, can you talk a little bit?
Very
Go
good.
ahead and just continue with the discussion. And we'll just
Okay.
we'll ask people.
So we're going back to
Okay, so it was just a laptop issue. It's different.
Yeah, the max.
But if they're unhappy, they would say that.
Yeah. So
He would say that now.
Actually, listen to Henry as it is.
Okay, good. Go ahead.
okay, so we were talking about the debate about left and right brains and how the left side is the analytical and the right side is the more creative. And that kind of goes with building a supercomputer because you always need people who are doing more innovation, exploring new ways of building these machines. And then at the same time, you need people who can build solid machines that they can run on today's technologies to do all the work that we need. And from there, you can see so just from that opinion, we can look at technical people. So yeah, we can think about researchers and technical people who are working in the field, and also like when I say technical in here, I'm somehow maybe mistakenly or wrongfully combining the computer science researchers in this who work on creating new things with these HPC systems. So we need to be creative, at the same time we need to be analytical and come up with the best designs for our systems. And that takes me to computational science versus computer science, which they also touched on yesterday. So for computer scientists, they are the guys who break our systems most of the time. They want to run in different ways, and they want to explore new things, while computational scientists are the guys who are. We have an art pick over here. So for computational science, they use our resources and supercomputers to process their today's problems, to find the solutions for tomorrow. So they can do genome sequencing or chemistry, nuclear, whatever it is that they want to do. So that is the difference between these guys. So look at the design, what makes a supercomputer, and then we mentioned a view of computers. So what is the difference between these guys? We can talk about it in a second. And what we need to do is we need a space or a place to do the computation itself. And that will be our compute nodes, and then we will need a network to connect all of these components together, and that will be maybe Ethernet or an InfiniBand or a combination of both. And then we need storage. So you can look at your nodes and look at them and see, when Henry gave the tour on Sunday, he was talking about all of these machines, the nodes that they had, each one of them had a 1 terabyte disk. Why did they have a 1 terabyte disk? It's because of that's how much money they had, and maybe that's the default setup for the server when they purchased it. And then from there we can move to batch schedulers and cluster management and orchestrators. How do you combine all of these resources together? When you have hundreds or thousands of nodes, you will need a way to manage all of these. And then the last part will be the HPC software plus some miscellaneous stuff. And we look here, and the question will be, what's in the pizza box? Because we call these servers or nodes pizza boxes. So you can see that this is a fully functioning Linux box. It's loading, and all of this is working. Your node can contain, for sure, some CPUs, maybe some GPUs. It depends on the size, and then memory. It depends a lot or small. Sometimes what you do is you will build very basic model of a lot or of a lot of basic nodes with just the standard CPU, memory, disk full or disk less. And then you would have a smaller number within the same cluster that can carry on GPUs or maybe much more memory, so we call it big RAM or stuff like that. And then comes the disk full versus diskless, and the thing with these guys will be, first of all, its price. When you go diskless, you will need more memory to load all of your operating system and these. Every reboot, every restart or reboot for your cluster means a new reinstallation for all operating systems for all of your nodes. So if you are talking about maybe Summit, that would be a lot of reinstallation at the same time for a full shutdown or restart for that cluster. So you need some management tools to deal with all of this. And for disk full, it can be slower because you are dealing with spinning disk most of the time, maybe some SSDs if you're lucky, and even these SSDs will be very small. So what can you do with it? When Henry was talking about the nodes that they had downstairs in the data center for research, you can look at, they had 600 something nodes. So when you talk about 650 nodes with 650 terabytes individually existing on these nodes, what do you do with them? Can you build some kind of parallel file system on these? Would that file system affect the performance of the nodes? And we'll talk about it in a second. The reason for these effects would be the network, because if everything is going across, the data has to move from somewhere. So for supercomputers, what really identify them to make them unique compared to other, let's say, industrial machines is the InfiniBand network. In supercomputers, we care about latency and bandwidth, but most of the time we're caring about latency more. So competitive technologies, InfiniBand can give us 1.5 microsecond versus the Ethernet, which can go up to 12, maybe more, depends. Now, as in bandwidth, the technologies are catching up, and they are doing almost the same speed. So we can see Ethernet like 100G today, even 200G. It goes down to 40G, 25, and then 10 or 1 gig, while InfiniBand is doing more like 40, which is really like 32 if they put it under 56, and 100 and now they're for 200 and 400G. What we are looking here is one of the Minimax big InfiniBand switches. So we have an older model at our center, and these are very nice. I really love it. These things are huge. Each one of these has 648 ports. It's amazing just seeing the connection and like the backplane of these switches. And then comes storage. So we talked about the internal storage of the machine. So we have disk-full versus diskless. But then we still need to have like a network shared file systems that users can access from everywhere while being on the cluster. So what we usually see is home directories, scratch space, and project space. And home directories are usually small. It depends on your center and policies and all of that. But most of the time, they try to keep it small to like 10 or 20 gig if you compare it to Exceed machines. So like here at OU, they are doing 20 gig. At our center, at UNL, for historic reasons, we've just deployed a new storage system, and we ended up setting our quota to 200 for home directories. And the reason was many of our users before had like limitless space because we started with very small users and it expanded. And as it increased, they kept like they were spoiled. So now we're trying. So now we are trying to train our users. So I'm being told that I need to be louder.
I don't think you're ever gonna be too loud.
Yeah.
I don't think that's possible.
I tried.
Volume there to max.
It starts to hear you Zoom options.
Huh?
It starts to hear you.
Oh,
Volume?
And then you turn it on for yourself.
He's talking about you saying the game.
I think he's talking about the
I
settings.
can't set it.
Oh, and the
Oh, I can try, but when we did that, it pegged. So
Right, but that was with your voice.
That was your voice.
okay, I'll do my
That
best.
channel is inner Henry.
Sorry.
Henry, use your indoor voice for a change.
What if you said it?
Yeah, I think
The automatic adjustment.
Okay.
just has one volume.
okay, so we're trying high volume here. I'm not sure if this is that works. So let's see.
Keep talking. Oh, sorry, yeah, just get rid of that.
Okay, yeah. So we go back to storage and the usage. So we talked about home directories, and then from here, we also look and we see most of the time there is a scratch space. In the old days, it was just an NFS export, which is just like a network attached file system that you export into all of your nodes on a centralized storage system, which also depends. Like you can run it with just like a very simple Linux box, or you can run like an enterprise storage and export it to that. So, and then from there we can see project space. And with project space, these are special requests that you can get from some of the users or like bigger research groups who wanted their data to be isolated and kept away from everyone else. Sometimes for compliance reasons, like when you talk about HIPAA stuff, or like HIPAA dealing with student. So HIPAA is dealing with medical and insurance records, and then HIPAA dealing with student records, if you're pulling some of your student data. And of course, we have export control when it comes to defense and like military stuff. And I'm not sure here, like most of you guys here work for supercomputers, so does anyone have an idea about the size of their home directories? Like what is your standard? What do you use?
100 gigs.
100 gig. So, huh?
7 terabytes.
No, wait, so 7 terabyte per user, or is it just like a
No,
space?
sure.
Oh, that's the size. Okay.
What are you asking the quota?
So I'm asking the quota, like, do you have any
We
limitation?
have a quota.
Yeah, so many of the systems, they just like, especially the older systems, people or admins prefer not to deal with quotas. And then what happens is you will end up dealing with maybe running some scripts or like run jobs to monitor the file system, which is painful. We had to deal with this in the past, and it just like it's so annoying. So dealing with quotas is much easier. And then scratch space. So, like, how do you guys deal with it? Like, does every project get its own scratch, or
I think we give 20 gigs as a quota, and we delete scratch space.
so you
Like the
decide
the archival process, images, we have a full tape machine for the entire thing that one just parse it up, and then we have, I think, daily, weekly, monthly, and then yearly that eventually replaces it after a couple of years.
How large is your quota?
I think it's like 20 gigs.
20 gigs?
Yeah.
I've got users that can't store their source code.
wow. So is that for weather modeling? that
It
you're
is for
talking about?
weather, yeah. Our typical output per day right now is on the order of a terabyte for a full day's runs on our project for one user.
So how many nodes is this user is using?
How many nodes?
Yeah, like as in compute power.
They're using, it depends on the piece of the workflow at the time, anywhere from 1 to 240. How large is your mass storage pool, and how large is your
I'm
user?
not sure the numbers past that.
So yeah, the question is to you then. What is the size of your storage if you're generating this much of data, and what kind of storage are you using?
I currently have a petabyte of high performance luster
Nice.
with an InfiniBand FDR backlink for the luster. And we're going to grow that next year to 2 petabytes.
So you're exporting your luster over InfiniBand to?
No,
it's-
yes, luster over InfiniBand back to the cluster.
Yeah.
And then the cluster is, of course, it's not really a cluster, it's a Cray supercomputer.
Yep.
With the Aries interconnect.
Mhm.
So we've got a lot of high performance. We actually have a scratch, and then we have a second tier that's also a high performance luster. But that one's on fiber channel, so it's much slower.
Yeah.
But that again, it's second tier. It can stand to be slower.
So that's like a 16 gig fiber channel on the back plane, or is it?
Yeah.
Yeah.
And our third tier is simply 10 gig Ethernet with all the latency that's implied here.
Nice. So what about your network? What do you have today?
Right now, we have what the researchers have on their own out spread out across the campus. We haven't done a true inventory of that yet because we're just trying to get all that kind of reined in to implement the science DMP. They're still kind of fearful that, is the ITS big brother coming to find out what we've got. So we're still kind of sending out, the surveys and trying to find out what's out there. Very little response from the research community.
So yeah, they are afraid of you. So I guess
They're afraid of us.
as they mentioned, if you shut down air conditioning and air cooling, maybe they'll start coming out and saying, "Oh,
Well, I'm not going to shut down AC because Alabama tends to get pretty hot, but we are implementing network access control, so they will have to register the devices on the
Yeah.
network to do it.
And of course, when they have their smaller clusters, like I've seen it before, where like research groups will go and design and sometimes even execute the purchase of a supercomputer on their own, or like a mini supercomputer, where like you're talking about a rack or less. What happens is they would go and buy something like missing components. Like it happened where we had a group and they bought their own system and they forgot to add InfiniBand at all. And the entire network within the cluster was 1G Ethernet. And I'm like, what do I do with this machine? They didn't know what to do with it. So they moved it to our center and they were like, okay guys, take it, fix it. And we've been running it since that time. But like, we still have to deal with these problems and you have something to say.
I'm obligated at this point to say the first cluster I built ran on 100 megabit Ethernet on a hub. 100 meg hub.
Oh, wow.
So that's a big wolf cluster, right? At that point, the definition of a big wolf cluster is using just like PC.
That was a true Beowulf cluster.
So yeah, a Beowulf. So we are talking about the InfiniBand network here, and let's go back to this. So InfiniBand is what identifies a supercomputer like these days. So if you look at a supercomputer with only Ethernet interconnects, especially like the slow ones, like what we are saying here, 100 meg or 1G, that would be a Beowulf cluster. And it's good for education. So what we did at UNM, we collected surplus PCs. So every time people go, like let's say the athletics department, business school, or whoever is throwing PCs, we had our student employees go collect these PCs and put them all together as one cluster. And we get some hand-me-down machines from Las Alamos Labs. And what we did is we had these big extreme switches that we connected them, and we had a cluster. And it had like maybe 200 nodes, 400 cores, and we used it for education. So like when we were teaching Hadoop classes or whatever, like other HPC courses, we were using these nodes. And it helps a lot. We didn't get much of it. Like if they broke something, you just reboot the machine, load the image again, and we're back to business. So it makes life easier and cheaper, especially for like new users, which Talansh was talking about yesterday. Is like he wanted to try new things. At the same time, you are expecting them to break things. So back to storage, we already hear cluster here. And there are two types of file systems. We have the traditional network file systems that we are using, and we have parallel file systems. So I just want to do a poll here in the room. How many people know that they are using parallel file systems, and what kind of PFS are you using? So what file system are you using?
GPFS.
GPFS. So
Yeah, from DD and storage.
Yep. So is that expensive? What
Yes, but
licensing?
it also has been very reliable and has good performance.
So what is the size of your storage team on site?
As in number of people?
Yeah, like people, how many people do you need to manage such a file system compared to, let's say, like we'll talk about, like, for example, Buster and other things. So we have people using different file systems. I would like to hear.
Yeah, I mean, for the most part, it's just me and my boss handling the storage, as well as many other
So
things.
wearing all the hats.
It would be more ideal if they had one person who managed just storage and could optimize it.
So can you tell us what else do you have? So you have your parallel file system.
We have, let's see, we have 4 clusters. 2 of them have DDN storage with GPFS.
Mhm.
The others have various storage devices with NFS.
Okay.
Okay.
Which is like the traditional part of it.
Yes, it is a non-parallel file system.
So what about the Lustre file system that you're using? It's a petabyte right now?
We have 2 Lustre file systems. We have a petabyte and 360 terabytes.
Nice.
Both of them are connected to the cluster. I've got some users that still use the slower file system,
Mhm.
simply because there's more space out there now.
Of course, yeah. So it becomes like speed versus.
And I have one user who, given enough time, and that's measured in days, not months, will fill up that smaller file system.
Yep.
Because the concept of data retention policy is completely wasted on that.
So I saw other people here. Yeah. So what do you have?
We have Orange FS and PGFS.
EGFS, the one from Jim.
Yeah.
Yeah. So how do you like that one?
We actually deployed it this year, and we deployed a test, a few servers just as a test scratch system.
So you have like a client or a few clients.
We have a few users who run massively parallel jobs, and we had them run it on that system to test performance.
Did you attach it to like an existing HPC system in production, or is it like the whole environment is testing?
It is in our current HPC system,
Okay,
so
so
end
it is
users
in
can
the
access it. But it's currently limited. We like it a lot, so I guess in our next maintenance period we're gonna expand it into the systems that currently now are stored in FSS.
Nice. So anyone else is using cloud systems?
GPFS on the cluster, but then we have a small Ceph cluster too that's running Ceph-FS.
Yeah.
That's kind of neat.
So you like stuff.
So far, it's been good for us with the S3 plugins
So
for sharing.
we built Ceph a long time ago. We built it on a machine with Penguin, and the idea was like the hybrid cloud and all of these. From our cluster was one of the first ones, and it wasn't the best one.
Yeah, we waited a while.
Okay, yeah, that's smart. I think it was their first one that they deployed, and we just took it as a test. Okay, so also when we say storage, we touch on the cloud, and what's happening on these days is a lot of vendors, they are providing you what you have on site. So you build your racks and all of that on site, and then from here you can burst. Well, so it's two things. You can gain more storage on the cloud as needed. So if you have like more jobs or more data to dump out of your, like let's say out of the scope of your system, like if you have 200 terabytes and you already generated that much and you're moving to much more, then you can move it to the cloud. Of course, you have to pay for it. Usually, when you go to cloud resources, getting your data in is very cheap. Getting it back is expensive, and that's why it's good. And then we need a resource manager and scheduler, and we have some different examples. Just like listed a few, and you can go both in the room and see what people are using. So today at our center we are using like I'm testing on another cluster like with the whole OpenHPC package. I'm playing with it with BGFS as we were talking a second ago. And the names keep changing, so like I honestly lose track because like I'm a network engineer who started to do HPC stuff and also involved in the storage, so like just wrapping your head around all of these changing factors is hard. It's like, so I don't know if anyone is using Moab in this room. Can you tell us about your experience with it?
Oh, it's okay because we have a very small cluster.
Yeah.
So it's working fine for us.
Nice.
I think it's similar to Talk.
Yeah, it is. As a concept, you can even embed it with Torque and PBS, so you can combine it as an external cluster management component. But yeah, so the scheduler, it decides what runs where, and then your resource manager, it oversees the available resources, and that's how you can assign the jobs and all of these things. And then software. So all of this, we built all of this for what? To run our simulations or jobs, what we call them. And for that, you need some customized HPC software because what you run on your laptop to do a small script doesn't really work the same way on a supercomputer. Some general use and some of them are custom for a specific application. So I don't know what is the most interesting things that you have here. What do you use, guys, in the room? Don't be shy. I want to see hands. Like, what do you use?
For
like just software packages that you usually use for different applications on site with your users.
like simulation software.
Yeah, like simulation or just running jobs or sequencing things.
NAMD.
So yeah. So do you have more packages that you're using?
Oh God, yes.
Yeah.
But NAMD and LAMPS is probably 90% of
Wow.
my user. It's 90% of my resource usage. It's not 90% of my community.
So what kind of research are you guys doing? Like your focus?
One of them is cancer drugs, I think, and the other one is some kind of materials that I don't really know about either.
Yep. And
Espresso, Gaussian, Labs, WASP. Are large users to run their custom codes.
So like you have them building their modules and all of that, and then deal with them. So how do you deal with software installations? Like we started using Stack, and that kind of made life easier. So does anyone else using some automation tool? But yeah,
Everything. TensorFlow has been a big one lately.
yeah. So, what about like here? Jason?
Well, our primary test cases are going to be primarily in chemical engineering and chemistry, and they're going to use a lot of calcium.
Yeah.
We also have some potential test cases from mathematics and biology where they want to do quite a bit of computation with R with large data sets.
Yeah.
Very large data sets, and also some kind of cluster aware packages from like Stata, for instance. They want to run the multiprocessor Stata and Mathematica and MATLAB and all that kind of stuff. So we have a lot of help for that.
So do you pay for the licenses from MATLAB? Because like all of these applications, once we start getting into these apps, it's more like you have to pay a lot of money in licenses.
We do, and we have, because of that, we have a lot of faculty who are trying to explore stuff like Octave, for instance, as an alternative to MATLAB.
Yeah.
And we're getting a lot of traction with that, with faculty wanting to use these packages in courses through like Jupyter Hub and stuff like that. So we're also trying to find ways to leverage our cluster to do kind of elastic on demand, for these services.
Yeah.
So looking into things like Kubernetes with containers and trying to have some kind of elastic demand there. But yeah, I mean, we're just sort of pretty nascent with our cluster, and we're trying to identify those initial use cases, and probably for the kind of true parallel computation, it will be a lot of Gaussian out of the gate.
So yeah, like most of the time what we see is like chemistry people, like chemistry, physics, nuclear, and biologists. These are like our 4 biggest groups of users, like as in a category. But we started to see more people coming from business school, or like from psychology and neuroscience. We had some users who processed more than 7,000 MRI images for patients, and they got like some weird, interesting results that they're still working on. I cannot talk about it. But you see interesting things, and this is what I love about this job is you look at stuff that you wouldn't even expect that people are doing or dealing with. And then there are some other components that we still need to touch on. So how do you make sure that your supercomputer as delivered is what you ask the vendor when you purchase that machine? Like it can do the job and all this, so you want to check on benchmarks. So that's one of the first thing that we do. Like you get a new machine. So like the process of buying a supercomputer depends on the policies of your organization. Usually you have an RFP, so you send a request for information, like RFI and then RFP, so you request information. And then after that you will get some designs and offers from vendors. Based on that you will make your general idea, and then they will make their bets on the lowest price, and you will make your choice. If you already built like a supercomputer that you wanted to expand on, usually you don't need to go through all of these processes. You can justify it and say that we are expanding, or maybe you have a contract of, like they say, on a life cycle, like what we've seen here. Like I think every 4 years you replace all your machine.
I'm sorry.
So like you replace your machines here every 4 years, right?
So that's the plan. I mean, right now things are being delayed a little bit, but in principle, yes.
So yeah, like we see some centers where they run on a planned life cycle, and then other centers who just like swing. That's what we do. Like most of the time we get hand-me-down machines from other national labs, and then in some cases we get bigger grants that we can build like smaller customized clusters. But benchmarks are one of the first things that you want to run on your machine, just to make sure that what you asked for, what you paid for, is what you got. And then we need, of course, some security and logging tools and devices. So we usually use some SSH gateways or something like that, two-factor authentication. Like people are using XCT, and I'm sure most of you are using XCT resources, or at least looked at it. So usually there is a group factor that you can go and authenticate who you are by email or cell phone. And they want to keep tracking who is on which machine. And the reason for that is these machines are so powerful. So if somebody breaks in or if they get compromised, then it's a disaster for real because you have all of that computing power that can be used for, let's say, Bitcoin mining or stuff like we've seen it before, like on a GPU cluster where people try to do this. So and other things would be like, your system is as weak as the weakest piece in that chain, and sometimes the end user laptop or machine, if it's compromised in a way or another, it can leak into your cluster. So you want to protect yourself from all of these, just like external factors. You want to monitor, and when I say monitoring utilities, we talk about things like, for example, something like Ganglia or like other machine, like other servers that you can build, or maybe even like small VMs you can build in your environment to monitor between hardware failures, cooling, components are going down, nodes are rebooting. I don't know if anyone else is using different tools. So do you use any monitoring tools for your systems, guys?
Okay, well, depends on what kind of monitor.
Yeah.
Nagios or like?
Nagios, yeah. So usually Nagios and Ganglia is what I've seen in production. And then there are backup systems, and usually these are the cheapest that we try to look at. So you can go to, they call it more like, just like tape libraries, they'll be the cheapest maybe. But the thing with tape libraries, it's more like you write it and you try to keep it set as it is for as long as you can. If the tape dies, then I guess it's dead. You can also archive it on like the nearline spinning disk, which is still not cheap enough to use it for like large amounts of data backups. We can go for the cloud, and cheaping it, storing a terabyte in the cloud can cost you maybe about 10 cents, something like that, depends. But retrieving it, you'll end up paying a few $1,000. Depends on the size that you are storing. Cooling systems, so we have the old air conditioning coolers, not so effective. And then you have like the chilled water, but then you need a facility that can deal with this. So like the new facility here at OU can do this, and it's all chilled water when we have the tool. You can go back and watch the video. So if you look above the racks, you can see all of these lines between cabling and water. And then backup power, here is the UPSs. So what happens if you lose power to your site? So smaller centers, sometimes they don't have anything else. So if you lose power, that's it, it's down. Other centers, they deploy UPSs. That's what I have in my center. We have 2 UPSs that divided between both of them. We can carry all the load of the machine home for compute for about 5 to 10 minutes. So we can initiate. So if you lose power, so we have monitoring tools that can tell us that, oh wait, we have a power outage. And what happens is we have scripts that would run in that case and would shut down all compute, and then storage takes the longest time, and that is the scariest. So a storage admin and power outage will be freaking out. And what happens usually is you would try to run your storage system as long as you can, because most of the time it's just like electricity flickering because of weather or something like that. But then at some point you have to decide, maybe in 20 minutes or something like that, do I shut down my systems? Do I keep them up? What is the risk of both of them? Because with spinning disk, going down after maybe spinning your disk for 5-6 years nonstop and going down, that is scary. Like you would lose, like it would be a cluster failure sometimes, and I've seen it before. And then licensing is what we talk about, like software. Do you run your own license server or look into exactly what cluster center does the one thing? What we are looking on here is just like a traditional HPC cluster. So just wanted to show it in a diagram, and I stole this one from VMware's blogs. And this is just like this is no virtualization of this one, but if you look at it, you will have a login point So your users are coming remotely from wherever they are. Sometimes we use VPN, like secure tunnels, to get into the system. Sometimes you just open into the world. You get into the system, and then you have a head node. That head node is controlling all like the orchestration of the cluster, and then from here you have your compute nodes. And then we have our traditional file systems, and you have your PFS at the same time. So that would be an example. And then another example that I found from one, this one explains a little more because it shows you how the jobs are being queued. So users are coming in, you have your admins are watching the system. And then from here you have the different components between health monitoring, licensing, storage, and network, all of these components. And then you have your jobs that are being submitted in queue. And whatever comes in the job, like you can have your jobs based on like first in, first out, or maybe based on project or the PI, how much money did they pay. So like sometimes what we do is we build a general machine, but then we have a few PIs who come and invest more. Like let's say PI comes to you and they add 10 nodes or 100 nodes. So what do? You want to open that resource for everyone, but at the same time you want to create a special queue for these people. So when they submit a job, they take advantage and their jobs just bypass all the queue and get submitted to their 100 machines or whatever they got, based on your policies and your deal with them. And then that's how your resources will be split between these jobs. And then virtualizing these systems. So virtualizing supercomputers is already in business. They have it. Different vendors are doing it in different ways. We have our like private virtual clouds. So SDSC, they have their own virtual environment. They did their testing. So when they built their machine, they didn't have that much of experience with virtual HPC. So what they did is they bought or rented some AWS nodes, and they did some studies on it. And when they submitted their grant proposal, they were like, okay, so here's our testing. That's what we did, and then that's to the best of our knowledge. The problem was there were no on the cloud with AWS until today. They don't have InfiniBand. So the problem was like, okay, I'm showing you all of this, but this is on Ethernet. So how does it work on InfiniBand? AWS would come and say, we have our enhanced network, which is something else. It's called like, it's an Ethernet network with something called SRIOV. But you're just adding a new layer that is your virtualization environment. In this case, it's VMware. And then you run all of your nodes and all of that the same exact way as you were doing in your traditional HPC. Now, the advantage of doing this in a cloud or virtualizing it is dividing your resources, utilizing it more. Because sometimes we see users who would come and take the entire node and they submit jobs, even though they're using one core of that node. So if you have people like that, it might be easier to virtualize it, give each VM maybe 2 cores or something like that. And then based on this, you reduce your losses and you can run more users. So that's one case. Another case is compliance. So we are working on a project right now on building a new like virtual environment. So it's a solution of different vendors that is called, and I'm not marketing anything here, but the solution is called FlexPod. So it's a combination of Cisco and NetApp between storage and data. And then you build VMs, and what you're using is VMware. You have all of these secured in a way where you isolate your environment. So we are building it for like an HPC compliant project. It helps. And then from here, we'll talk a little about time, because time is money and it's important. So like we think about a second, it goes like that. 10 seconds, we can think about them. 1,000 seconds, that's like what, 17 minutes. But then like how long a million seconds are. So we start saying these numbers, when we say million, billion, these are scary numbers. Like a million seconds are just like 17 minutes, so that's not much. Actually, it's 12 days, I mixed it up. But then last year I celebrated my billion years years in seconds. So that's like almost 32 years of passing of your life. So when you say a billion, that's like almost a half lifetime for someone of us. And when you talk about multiplying that, like going next, that would be like 32 billion years, something like that. So it's scary numbers. So if we had like an ape who started 31 million years ago, doing a computer problem, your computer will be just doing it like that. Like you'll be just processing all of these within seconds. And this is just like an explanation of the numbers and what do they people like, what is the measure that we use in supercomputers. So this goes just like, it's almost the same as we use with storage or like whatever the numbers that we do when we study algorithms and all that. So it's maybe next time we are going to exascale computing. So this is a better example to explain this. So CPU clock, we are talking about frequency. So when you buy a new processor, it will be something like 2 point something gigahertz, something like that. And then the clock speed in cycles will be in seconds and hertz. Number of floating points, operation per cycle, that's how you measure your HPC system's performance. And then the example here is if you got a 2.6 gigahertz processor, that will be 2.6 million cycles. If your processor, and this is on a specific vendor, so this is an Intel processor, it's the Haswell one. If it does like 16 floating points, then this is how much billion, which is in gigaflops. So you have one processor that can do 41.6 or almost 42 gigaflops. And that's how you can measure the performance with supercomputers. So just multiply this with how many cores or processors of this kind, or whatever kind you have. Just you plug it in this example and you can get your numbers. Based on this, we can see the top 500 history. So in 93, they had the first gigaflop that they were looking at, and then in 97, they had the teraflops. So it took, like you can see, it took maybe 5 years to go from here to there. And then 2008, it was the first betaflop. And from there, they moved to like 122 teraflops, and who knows. So this is Summit, and then who knows what's next. Like we'll be talking about this. So it keeps expanding. And the processing power itself, it's not increasing that much because how much can you fit? Like how many transistors can you fit at this time on a processor? Not like we cannot keep expanding that as before. We said like the most does not apply. So you have to scale out your machines to add more computing power. We talked a little about the cloud, so like I have some pros and cons. So it's cost and cost. If your center is new and you cannot afford building a new supercomputer, considering all the other factors like power, machine room, space, politics, all of that. If it's a small research group, then it might be cheaper to go to the cloud. We did the math at our center. If we go beyond 30% utilization, then it's not feasible to be on the cloud. Like if your machines, if your processors and memory and all of that is being used more than 30%, then it will be so expensive that we just like basically shut down. So it depends. But at the same time, we have special projects like where researchers would go on their own and they would buy some cloud time and start processing their data. That would be cheaper for them. It depends. So yeah, being on the cloud, its cost can be effective or not effective, depends on your case. It's easier to build like most of like Azure, Google, AWS, these days they allow you to build, like they provide you with the tools, so you can easily.
Have you played with Azure yet?
Not yet. I'm looking at AWS.
Yeah, Azure does have Infinity.
Yeah, so that is the difference. And I actually talked to Amazon and I was like, what do you think, guys? Like, and they have their own opinions about their network. But yeah, Azure, like they are way ahead in this game, at least what they have announced publicly.
Azure is actually looking at a science business model, and Amazon seems to be looking more at a business type business model.
Yeah, which goes back to the presentation that we saw yesterday about the networks. And it's like how much money do you want to spend for what do you get out of that? So the same thing for these cloud providers. If the market is small, even if you look at their HPC teams, like if you go to AWS and look at their HPC specialist team, it's very small, it's very new, like they're just learning it. Same thing applies to all of the vendors. They're starting working on these things. Another thing would be cloud bursting. So you start your jobs here, you exceeded your resources, your local resources, you can start bursting into the cloud. Vendors these days, they are putting more investment in it. Parts of the cons will be compliance. Does your institute allows you to move to the cloud? It doesn't make any sense. Like now we have the government cloud, which is basically an AWS secure environment and like approved and following some NIST standards. You'll be a vendor specific. So let's say if you move everything today from your HPC center, which also applies to enterprise IT, to a specific vendor, but then 2 weeks later they will raise their prices. What do? Do you move to another vendor? Are you stuck based on your contract? What happens next? That's a big problem. And then it's also harder to track for the institute. So at our institution, one of our problems is we try to probe and see who's using what cloud resources and how can we provide this or maybe combine it or give them a solution in between. And that started a big political of ideas on the case. You cannot go to a vendor and ask them people are using maybe their private email accounts, so even based on their like institutional email, you cannot tell. And then quantum computers. I took this picture of the IBM quantum computer at supercomputing last year, and it looks amazing. It looks so nice. I guess most of the people in the computing field, they still don't understand what a quantum computer is, including myself. So if it can help, I would take that help. So anyone can tell us what quantum computer is.
I've asked actually several quantum experts. Yeah. And the response I've gotten is not interpretable by mere humans. You gotta run them really cold.
Okay.
That's about as far as I've ever gone.
So how do you cool it?
Liquid helium, normal helium, and below. Yeah.
So yeah, I guess it would take us a lot of kids. So what they call the smallest unit in a computer is just like a bit, which is a binary 0 or 1. And then in quantum computers, what we have is a qubit, and that would be a 0 or a 1 in a quantum state, but it can be both in the superposition state, and then it takes a probability. And based on that probability, you will get your 0 or 1 at the end of it. So your bit can be either, but based on numbers and how it was stored and other factors in the quantum space, that would, I don't want to make any other statements about this, because I can't say much. From here, we'll talk about the resources that are available for us, all of us today, especially for smaller centers or for very large projects. The sequence of these machines it's not necessarily based on size. So it's just what I found on my Excel account, and these are the resources that I have access to. So it tells you the supercomputer name and then the center that is hosting that supercomputer, and all of this is nationally funded. It's open for research. If you are an Exceed Campus champion, you will get startup allocations on all of these machines, and your allocation will be dedicated for your researchers. So the idea is to help the campus champion, help their campus start using and utilizing these resources before they apply for fully loan grants on this. Helps them to decide if do I really need to run on such a big machine or not. And then the other factor is you have some numbers to show your pilot project to Exceed and NSF and say, okay, I've done my homework, please give me more education on these machines. And presentation. So, again, my name is Hussein. I work for the UNM Supercomputer Center. Here's my LinkedIn link if you want to add me there. And I don't know if you have any questions.
I have one comment.
Yes.
If you end up designing one of these systems and you have a backup power system for your cluster, make sure your cooling is also on the backup system. Otherwise, it's not going to do you any good.
Yeah. So it happened to me before where we had power outages. Luckily, it was in winter in Albuquerque, and what happened is we went and we opened the back door of the machine, and we just kept it open. So it doesn't rain in winter in Albuquerque, so it's a good thing to have. So we just had the back of the entire machine room open to the cold air because, yeah, we had a failure in the machine room. So things can happen.
Do we have time for me to add a story along this same line?
Technically, we're in coffee break now, but.
Okay, I am not going to get in the way of people and coffee.
What OS do you run on your edge?
So we run Linux CentOS. So we run the
CentOS?
yeah. So you can, if you probe everyone, it will be mostly Linux. Like I've seen maybe one or two supercomputers that are running Microsoft.
There was one at University of Virginia that was brought up on Mac OS. There was one in that part of the world brought up on Windows. There are a handful of Windows HPCs and systems out there. But most of the Microsoft implementations now, they come in and they say, oh yes, and we have this Linux implementation we're going to put on.
Yeah.
Which is good. Yes, but that's a change in the last 2 years. Microsoft, we have a kinder and gentler Microsoft right now.
The culture is changing. Yeah, the culture in Microsoft is changing. They're supporting more, like I've seen them supporting much more open source projects, and they try to utilize it. Even internally, they're using more Linux.
Well, they're supposedly Windows 11 or 12 is going to be Linux with a Windows GUI.
Oh, that's, yeah. So Don?
So the entire Microsoft Azure platform, cloud platform runs Linux underneath, Windows on top of it. So, entire base.
Is that how it is now?
So, coffee break?
So
I'm having my coffee and I finished the cups.
Some bullshit.
All right.
I didn't realize. Yeah, and now we end up really understand this. They sure can be.
Like, we have now 7 billion.
I have something. You're talking about making sure your cooling is on your